take a deep breath, settle into your chair, let your mind wander from whatever deadlines are chasing you today, because for the next while, we're going to explore something that makes your morning commute seem rather insignificant. Time moves differently when you're contemplating infinity, so forget about checking the clock. What you're about to discover will reshape how you see everything around you. You think you know the universe. You learned about planets in elementary school, maybe memorized the names of a few constellations, heard about the Big Bang in passing. But what they taught you was the sanitized version, the cosmic equivalent of showing someone a postcard of the ocean and claiming they understand the depths. The real universe is far stranger, more violent, and infinitely more fascinating than anything that made it into your textbooks. There are stars out there that shouldn't exist according to our best theories, yet there they are, burning bright and mocking our understanding. There are regions of space where the very concept of time becomes meaningless. There are objects so massive that they bend reality itself, and phenomena so bizarre that describing them sounds like the ravings of a madman. Yet every word you're about to hear is backed by careful observation and rigorous science. The universe doesn't care about your comfort zone. It operates on scales that dwarf human comprehension and timescales that make our entire civilization look like a brief flicker. But understanding it, even partially, changes something fundamental about how you see your place in existence. So let's begin with something that sounds simple, but isn't. What exactly is the universe made of? Your school probably taught you about atoms, protons, neutrons, electrons, the building blocks of matter. Except here's the thing that would have blown your teenage mind. Everything you can see, touch, or interact with makes up less than 5% of the universe. 5%. The chair you're sitting in, the device you're watching this on, your body, the earth, the sun, every star visible in the night sky, every galaxy we can photograph with our most powerful telescopes, all of it combined represents a tiny fraction of what's actually out there. It's like being told that everything you thought was real is just the foam on top of an ocean you can't see. The rest, 27%, is something called dark matter, and 68% is dark energy. These names aren't poetic metaphors, they're admissions of ignorance. We call them dark because we literally cannot see them, cannot touch them, cannot directly detect them with any instrument we've ever built. Yet we know they're there because without them, nothing else makes sense. Consider dark matter first. In the 1970s, astronomer Vera Rubin was studying how galaxies rotate. She expected to find that stars farther from the galactic center would orbit more slowly, just like planets farther from the sun take longer to complete their orbits. But that's not what she found. Stars at the edges of galaxies were moving far too fast. They should have been flung out into space long ago, yet there they were, held in place by some invisible gravitational force. The math was undeniable. There had to be roughly 5 times more matter in each galaxy than what we could see. Matter that doesn't interact with light, doesn't form planets or stars, doesn't clump together the way normal matter does. It's everywhere, passing through you right now as you listen to this, completely unnoticed by your senses. Think about what this means for a moment. You're surrounded by a universe full of something you cannot perceive. It's not hiding in distant galaxies. Dark matter particles are streaming through your body at this very instant. Billions of them every second, and you feel nothing. It's like being told that ghosts are real, except these ghosts have mass and shape the very structure of cosmic architecture. Scientists have built increasingly sensitive detectors, buried them deep underground to shield them from other particles, and waited patiently for dark matter to reveal itself. Some experiments claim to have detected faint signals that might be dark matter interactions, but the results remain controversial. Other detectors, built with different technologies, see nothing at all. After decades of searching, dark matter remains stubbornly invisible. This has led some physicists to propose that dark matter isn't made of particles at all. Perhaps our understanding of gravity is incomplete. Perhaps the equations that work so well in our solar system break down over galactic distances. Modified gravity theories have been developed that attempt to explain galactic rotation without invoking invisible matter, but they struggle to explain other observations, like the way light bends around galaxy clusters. The galaxy cluster known as the bullet cluster provides some of the strongest evidence for dark matter's existence. This system formed when two massive galaxy clusters collided at incredible speed. The collision separated the normal matter, which interacted and heated up during the impact, from the dark matter, which passed through unaffected. We can see this separation by mapping where the gravity is strongest compared to where the visible matter ended up. The gravity centers don't match the matter centers, strongly suggesting that most of the mass is indeed invisible. But dark matter, mysterious as it is, at least behaves somewhat predictably. It clumps together gravitationally, forming invisible scaffolding that regular matter uses to build galaxies. Dark energy is far more unsettling. It's the reason the universe isn't just expanding, but accelerating its expansion. Every second, the space between distant galaxies grows larger, and this growth is getting faster. The discovery of cosmic acceleration was completely unexpected. In the 1990s, two teams of astronomers were studying distant supernovae, hoping to measure how much the expansion of the universe was slowing down due to gravity. They assumed that gravity would gradually halt the expansion, eventually causing the universe to collapse back in on itself in a big crunch. Instead, they found that the expansion was speeding up. Picture the universe as a balloon being inflated, except the person blowing it up is gradually increasing their lung capacity. Galaxies aren't moving through space away from each other. Space itself is stretching, carrying them along. In the distant future, this acceleration will make the universe a very lonely place. Galaxies will drift so far apart that beings in one galaxy won't be able to see any others. The night sky will be empty except for their own local stars. But here's where it gets truly strange. Dark energy appears to be a property of space itself. Create more space and you get more dark energy. It's as if empty vacuum has weight, has substance, has the power to push things apart. Einstein originally proposed something like this in his equations, called the cosmological constant, then later called it his greatest mistake when observations suggested the universe was static rather than expanding. Turns out he might have been more right than he knew. The amount of dark energy in any given volume of space is incredibly small, far less than the energy in a single photon. But space is vast, and when you add up all that empty volume, the total energy becomes enormous, enough to accelerate the expansion of the entire universe. It's like having a force so weak you can't detect it in a laboratory, but so persistent that it eventually overwhelms gravity itself on cosmic scales. Some theories suggest that dark energy might not be constant over time. If it grows stronger, the universe could enter a phase called the Big Rip, where the expansion accelerates so rapidly that it tears apart galaxies, then stars, then planets, then atoms themselves. If dark energy weakens or changes sign, the universe might eventually collapse back into a big crunch. We simply don't know enough about its nature to predict its future behavior. This is the universe we actually inhabit, not the neat, comprehensible cosmos of textbooks, but a reality where the vast majority of existence is invisible and where space itself is an active participant in cosmic evolution. And this is just the beginning of the strangeness. Let's talk about time. In school, you learned that time moves at a constant rate. 1 second follows another in orderly fashion, the same for everyone everywhere. This is perhaps the most useful lie ever taught because it lets you function in daily life without your brain melting. But time, like so much else about the universe, refuses to behave the way our intuition demands. Einstein's revelation was that time and space are joined together in something called space-time, and massive objects warp this fabric. The more massive the object, the slower time moves in its vicinity. This isn't theory. It's been measured with atomic clocks on airplanes, observed in the orbits of satellites. GPS in your phone has to correct for time dilation effects, or it would be off by miles. The satellites orbiting Earth experience time slightly differently than we do on the surface. They're farther from Earth's gravitational field, so time passes a tiny bit faster for them. Without correcting for this effect, GPS coordinates would drift by about 6 miles per day. Every time you use navigation, you're relying on calculations that account for the warping of space-time, but Einstein's insights pale next to what happens near the universe's most extreme objects. There are places where matter has collapsed so completely that it punches a hole in space-time itself. We call them black holes, though that name barely captures their reality. They're not holes you could fall into. They're regions where the normal rules of physics simply stop applying. The formation of a black hole is one of nature's most violent processes. When a star, more than about 25 times the mass of our sun, reaches the end of its life, it faces a catastrophic fate. The star has been held up by the outward pressure created by nuclear fusion in its core, but when the fuel runs out, gravity wins decisively. The entire core, containing more mass than our sun, collapses from the size of Earth to a point in less than a second. The collapse happens so fast that not even light can escape the implosion. The outer layers of the star, still falling inward, slam into the incredibly dense core and rebound in a supernova explosion that can be seen from billions of light years away. But the core itself continues collapsing, becoming so dense that it warps space-time into a closed loop. Nothing that falls past a certain boundary, called the event horizon, can ever escape. At the edge of a black hole, called the event horizon, time slows to a crawl relative to the outside universe. If you could somehow watch someone fall past this boundary, you'd see them slow down, redden, and eventually fade from view, frozen at the moment they crossed over. But from their perspective, nothing unusual happens. They continue falling normally, unaware that the outside universe is racing forward at incredible speed. This creates a paradox that troubled Einstein. If you watch someone fall into a black hole, you never see them actually cross the event horizon. They appear frozen just outside, slowly fading away as their light becomes increasingly redshifted. But from the falling person's perspective, they cross the horizon in finite time and continue falling toward the center. Both perspectives are equally valid, yet they seem to describe completely different realities. Inside the event horizon, our understanding breaks down completely. The mathematics suggest that all the matter that ever fell in gets compressed to a single point of infinite density called a singularity. But infinity doesn't belong in physics. It's a sign that our theories are incomplete, that something fundamental is missing from our understanding. Recent research suggests that singularities might not actually exist. Quantum effects that become important at incredibly small scales might prevent the formation of true infinities. Instead of a point of infinite density, the core of a black hole might be something stranger still, a region where space and time themselves break down into discrete units, where the smooth fabric of space-time gives way to a granular foam of quantum fluctuations. What's truly unsettling is that black holes aren't rare cosmic curiosities. There's one at the center of every major galaxy, including our own. The black hole at the heart of the Milky Way has a mass 4 million times that of the Sun, and it's currently dormant, barely feeding. We know it's there because we can watch stars orbit around it, following elliptical paths that bring them to within a few light hours of something invisible. One star, designated S2, completes an orbit around our galaxy's central black hole every 16 years. At its closest approach, it moves at more than 5,000 miles per second, fast enough to cross the continental United States in about a minute. The gravitational forces are so strong that the star's light becomes measurably red-shifted as it climbs out of the black hole's gravitational well, providing direct confirmation of Einstein's predictions about gravity and time. When black holes do feed, actively pulling in surrounding matter, they become the brightest objects in the universe. Material spiraling into them heats to billions of degrees and creates jets of particles that can be seen from billions of light years away. These active galactic nuclei, called quasars, were much more common in the early universe, when there was more gas available for black holes to consume. The jets produced by feeding black holes are among the most powerful phenomena in nature. They accelerate particles to nearly the speed of light and shoot them out in narrow beams that can extend for millions of light years. The energy in these jets comes from the rotation of the black hole itself. As matter falls in, it gets caught up in the black hole's spin and twisted into a spiral pattern that launches material outward along the rotation axis. These supermassive black holes appear to regulate star formation in their host galaxies. Too much activity from the black hole, and it blows away the gas needed to make new stars. Too little, and the galaxy grows out of control. Somehow, these cosmic monsters maintain a delicate balance that allows galaxies like ours to exist in the first place. The mass of the central black hole is directly correlated with properties of the surrounding galaxy, suggesting a deep connection between the two that we're only beginning to understand. But black holes have an even stranger property that challenges our most basic assumptions about information and reality. According to quantum mechanics, information can never be truly destroyed. If you know the precise state of every particle in a system at one moment, you can in principle calculate what that system was like at any point in the past or future. Yet anything that falls into a black hole appears to be lost forever, taking its information with it. This creates what physicists call the information paradox. If information can be destroyed, then the universe is fundamentally random at its deepest level. The future would be unpredictable, not because we lack sufficient data, but because the data itself can be erased from existence. This conflicts with the basic principles of quantum mechanics, creating a crisis in our understanding of physical law. Stephen Hawking's contribution to this puzzle was the discovery that black holes actually evaporate, slowly radiating away their mass as heat. The mechanism involves quantum fluctuations near the event horizon. Empty space isn't truly empty, but filled with virtual particle pairs that briefly pop into existence before annihilating each other. Near a black hole, one particle from such a pair can fall in while the other escapes, appearing as radiation. The temperature of this Hawking radiation is inversely related to the black hole's mass. Larger black holes are cooler than smaller ones. A black hole with the mass of our sun would have a temperature of about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills space. Such black holes actually absorb more energy from their surroundings than they emit, causing them to grow rather than shrink. But smaller black holes would be much hotter. A black hole with the mass of a mountain would have a temperature of billions of degrees and would evaporate in a fraction of a second, releasing the energy equivalent of millions of hydrogen bombs. Fortunately, we know of no natural process that could create black holes this small, though some theories suggest they might have formed in the early universe when conditions were much more extreme. The supermassive black holes at galaxy centers will take an unimaginably long time to evaporate. A black hole with 1 billion times the mass of the sun will persist for more than 10 to the 90 power years, a time span so vast that writing it out would require more digits than there are atoms in the observable universe. But evaporate they will, and when they do, what happens to all that trapped information? Some theories suggest that information is somehow preserved in the radiation the black hole emits, encoded in ways we don't yet understand. The radiation might appear random to us, but contains subtle correlations that preserve the information about everything that ever fell in. Other theories propose that black holes are connected to other regions of space-time through wormholes, and the information emerges elsewhere, possibly in another universe entirely. Still, others question whether information conservation is as absolute as we thought. Perhaps the fundamental laws of physics allow for true randomness, true creation, and destruction of information. This would mean that the universe is not a deterministic clockwork where the future is fixed by the present, but a genuinely creative system where new possibilities can emerge and old realities can vanish forever. The implications ripple outward into questions about the nature of consciousness itself. If information can be destroyed, then the pattern of thoughts and memories that constitute your mind might not be permanent features of reality. If information is conserved, then in some sense, every conscious moment is eternal, encoded forever in the quantum state of the universe. While physicists debate these cosmic mysteries, astronomers have discovered that our universe contains objects that challenge our understanding in more direct ways. There are stars that shouldn't exist, whose very presence forces us to reconsider what we think we know about stellar evolution and the limits of what's possible in nature. Most stars follow predictable patterns. They're born in clouds of gas and dust when gravity overcomes the outward pressure of heat and turbulence. Nuclear fusion begins when the core becomes hot and dense enough and the star settles into a stable equilibrium between gravitational collapse and radiation pressure. The star's mass determines its fate. Smaller stars burn slowly and steadily for trillions of years, while larger stars burn brightly and die young in spectacular explosions. This standard model of stellar evolution works well for the vast majority of stars we observe, but there are exceptions that refuse to fit the pattern. Objects so extreme that they challenge our understanding of stellar physics and the fundamental limits imposed by nature. Consider Eta Carinae, a monster star system in the southern sky that represents one of the most unstable and dangerous objects in our galaxy. With a combined mass more than 150 times that of the Sun, it sits right at the theoretical limit for stellar size. Stars this massive should blow themselves apart long before reaching such extremes. The radiation pressure from nuclear fusion should overcome gravity and disperse the star's outer layers into space, yet there it sits, somehow holding together despite forces that should tear it apart. In the 1840s, Eta Carinae underwent what astronomers call the Great Eruption, an event so violent that it briefly became the second brightest star visible from Earth, despite being more than 7,000 light-years away. The eruption ejected several times the mass of our Sun into space at speeds of hundreds of miles per second, creating the beautiful but ominous homunculus nebula that surrounds the star today. The energy released during this eruption was comparable to a supernova explosion, yet somehow the star survived. Most supernovae completely destroy the star that produces them, leaving behind only a neutron star or black hole. But Eta Carinae emerged from its great eruption still intact, still massive, still unstable. It's as if the star tried to explode but couldn't quite manage it. Current models suggest that Eta Carinae is actually a binary system containing two massive stars locked in a tight orbit around each other. Their gravitational interaction creates tidal forces that strip material from both stars and fling it into space. The system loses mass equivalent to our entire Sun every few thousand years, yet remains massive enough to be considered hypergiant. The interaction between the two stars also creates complex patterns in the ejected material. The homunculus nebula isn't a simple sphere of gas expanding uniformly outward. Instead, it's shaped like an hourglass or dumbbell, with dense lobes of material separated by a thinner equatorial disk. This structure suggests that the eruption was directed by magnetic fields or rotational forces that channeled the explosion along specific directions. But even a binary system can't fully explain Eta Carinae's behavior. The star continues to show signs of instability, varying in brightness over periods of years, and occasionally producing smaller eruptions. It remains one of the most luminous stars in our galaxy, pumping out energy at a rate 5 million times greater than our Sun. At this rate, it's burning through its nuclear fuel at an unsustainable pace. The system is likely to explode as a supernova sometime in the next million years, an event that will be visible during the day from Earth despite the vast distance. But this won't be an ordinary supernova. Stars as massive as Eta Carinae are thought to produce hypernovae, explosions that release 10 to 100 times more energy than typical supernovae. The gamma rays from such an explosion could potentially damage Earth's ozone layer even from thousands of light years away, the existence of stars like Eta Carinae forces astronomers to revise their models of stellar evolution. These objects push the boundaries of what's physically possible, existing in a regime where radiation pressure, gravity, magnetic fields, and stellar winds all play crucial roles in determining the star's structure and behavior. Understanding them requires sophisticated computer simulations that account for complex three-dimensional flows of gas and magnetic fields. Even stranger are stars that appear to be older than the universe itself. When astronomers measure the age of the universe using the cosmic microwave background radiation, they get a figure of about 13.8 billion years. This represents the time that has passed since the Big Bang, when space and time themselves began. Nothing in the universe can be older than this, yet some of the oldest stars in our galaxy appear to have ages that approach or even exceed this cosmic timeline. These ancient stars, found in globular clusters and the galactic halo, contain almost no elements heavier than hydrogen and helium. Their chemical composition reflects the conditions that existed in the early universe when only the lightest elements had been forged in the Big Bang. Determining the age of a star requires understanding its internal structure and the rate at which it burns nuclear fuel. This depends on the star's mass, chemical composition, and the efficiency of energy transport from its core to its surface. For stars with very low metal content, these calculations become increasingly uncertain because we have limited experience with such objects. The most likely explanation for the apparent age discrepancy is that our models of stellar evolution are incomplete, particularly for stars that formed when the universe was very young and contained almost no heavy elements. These stars may burn their fuel more efficiently than we think, or they may have undergone mixing processes that altered their surface composition over billions of years. But what if the discrepancy is real? What if some stars really are older than we think the universe is? This could mean our understanding of cosmic chronology is fundamentally flawed. Perhaps the Big Bang wasn't the absolute beginning we think it was. Perhaps the universe has gone through cycles of expansion and contraction, with some stars surviving from previous iterations. Or perhaps time itself behaves differently on cosmic scales than we assume. These possibilities push us toward even more unsettling questions about the nature of cosmic time and causality. Our entire understanding of the universe's history is based on the assumption that time flows uniformly and that cause precedes effect. But general relativity shows us that time is relative, that it can slow down or speed up depending on gravity and motion. On cosmic scales, with masses and energies beyond anything we can directly experience, might time itself behave in ways we haven't anticipated? If the universe is truly infinite in space, as many models suggest, then every possible arrangement of matter occurs somewhere. There are regions of space where Earth's history played out exactly as it did here, and other regions where it unfolded differently in every conceivable way. In an infinite universe, there are infinitely many copies of you listening to these words right now, and infinitely many versions where you made different choices at every moment of your life. This isn't science fiction speculation, it's a logical consequence of infinity combined with the finite number of ways particles can be arranged within any given volume of space, if space goes on forever. And if matter is distributed roughly uniformly on large scales, then repetition becomes mathematically inevitable. Every possible book will be written somewhere. Every possible song will be composed. Every possible conversation will occur. Some of those alternate versions of reality differ from ours in trivial ways. Perhaps in one universe, you chose coffee instead of tea this morning. In another, you wore a different shirt. But other versions are radically different. There are regions where evolution took entirely different paths, where intelligent life never emerged, where the laws of physics themselves might be subtly different. The concept becomes even more bizarre when combined with quantum mechanics, which suggests that reality branches at every quantum event. Every time a particle's position or energy is measured, every time a quantum system interacts with its environment, the universe splits into multiple versions, each representing a different possible outcome. Most of these branches are nearly identical, differing in the state of a single electron or photon somewhere. but over time, the differences accumulate. In some branches, the asteroid that ended the age of dinosaurs missed Earth entirely. In others, different mutations occurred during human evolution, leading to species with different capabilities. In still others, historical events unfolded along entirely different timelines. If both infinite space and quantum branching are real, then every possibility that isn't explicitly forbidden by the laws of physics exists somewhere in the vast ensemble of realities. But even if you find such concepts too abstract to matter, the universe has plenty of concrete strangeness to offer. Consider neutron stars, objects so dense that a teaspoon of their material would weigh more than Mount Everest. These are the cores of dead stars, crushed down to the point where protons and electrons are forced together into neutrons, creating matter unlike anything found naturally on Earth. The formation of a neutron star begins with the death of a massive star in a supernova explosion. When the star's core collapses, it becomes so dense that atomic nuclei can no longer maintain their structure. Electrons are crushed into protons, creating neutrons and releasing enormous numbers of neutrinos. The collapse happens so rapidly that the core overshoots its equilibrium size and bounces back, creating a shock wave that blasts away the star's outer layers. What remains is a sphere of neutron-rich matter about 12 miles across, containing more mass than our Sun. The density is so extreme that atomic nuclei touch each other directly, creating a continuous sea of nuclear matter. A sugar cube-sized piece of neutron star material would weigh as much as all of humanity combined. Neutron stars pack more mass than the Sun into a sphere only about 12 miles across. Their surface gravity is billions of times stronger than Earth's. Drop a marshmallow onto a neutron star, and it would hit the surface with the energy of an atomic bomb. The magnetic fields around some neutron stars are trillions of times stronger than anything achievable in terrestrial laboratories, strong enough to distort the shapes of atoms themselves. These magnetic fields accelerate charged particles to nearly the speed of light, creating beams of radiation that sweep across space like lighthouse beams. When these beams point toward Earth, we detect them as pulsars, cosmic clocks that tick with incredible precision. The fastest known pulsar rotates 716 times per second, faster than a kitchen blender despite having more mass than the Sun. The discovery of pulsars in 1967 initially baffled astronomers. The signals were so regular and artificial looking that the research team briefly considered the possibility that they were detecting communications from an alien civilization. They jokingly referred to the first pulsar as LGM-1 for Little Green Men. But as more pulsars were discovered, it became clear that they represented a new class of natural object. Pulsars keep time more accurately than the best atomic clocks on Earth. The most stable pulsars vary by less than 1 part in a million billion over years of observation. This precision makes them useful as cosmic timing systems, allowing astronomers to test fundamental physics in extreme environments that cannot be replicated on Earth. The surface of a neutron star would be utterly alien to human experience. Gravity is so strong that the surface is perfectly smooth. Any mountain more than a few millimeters tall would be crushed immediately. The atmosphere, if it exists at all, would be only a few inches thick and composed of exotic particles that don't exist under normal conditions. The intense magnetic fields create their own strange phenomena. In the strongest fields, the vacuum itself becomes birefringent, meaning that light waves oriented in different directions travel at different speeds. This effect, predicted by quantum electrodynamics, causes the polarization of light to rotate as it passes through the magnetic field, providing astronomers with information about the field's strength and structure. Deeper inside the neutron star, the physics becomes even more extreme. The outer crust consists of atomic nuclei arranged in a crystalline lattice, but these nuclei contain far more neutrons than any atoms found on Earth. As you go deeper, the nuclei become increasingly neutron-rich and eventually merge into a continuous fluid of neutrons. The core might contain matter in states that can't exist anywhere else in the universe. At the densities found in neutron star cores, some theories predict that neutrons themselves break down into their constituent quarks, creating a strange form of matter called quark soup. Other theories suggest the formation of exotic particles like hyperons or kaon condensates, states of matter that push the boundaries of known physics. When neutron stars collide, they create some of the most violent events in the universe. These collisions were predicted decades before they were observed, as the inspiraling objects lose energy to gravitational waves and spiral closer together. The final moments before merger involve objects more massive than the Sun orbiting each other hundreds of times per second at a significant fraction of the speed of light. The collision itself forges heavy elements like gold and platinum in quantities that dwarf anything possible in stellar cores. A single neutron star merger produces more gold than a star like our Sun could create in its entire lifetime. The collision also creates a kilonova explosion that can be seen from billions of light years away, glowing from the radioactive decay of freshly minted heavy elements. The gravitational waves produced by these mergers ripple through space-time itself, distorting the fabric of reality as they pass. These waves travel at the speed of light, carrying information about the collision across the universe. We've recently learned to detect these ripples using interferometers that can measure changes in distance smaller than 1/10,000th the width of a proton. The detection of gravitational waves has opened up an entirely new way of observing cosmic events. Unlike light, which can be absorbed or scattered by intervening matter, gravitational waves pass through everything essentially unimpeded. They provide direct information about the most violent and energetic events in the universe, phenomena that would be invisible to traditional telescopes. But neutron star collisions are gentle compared to the universe's most powerful explosions. Gamma-ray bursts are flashes of energy so intense that a single burst can outshine the entire rest of the observable universe combined. They release more energy in a few seconds than the Sun will produce over its entire 10 billion year lifetime, concentrating this energy into narrow beams that can be detected from the most distant reaches of space. The first gamma-ray burst was detected on July 2, 1967, by the Vela satellites, military spacecraft designed to monitor nuclear weapons tests during the Cold War. The satellites detected a flash of gamma rays that clearly didn't come from Earth or the Sun. The discovery remained classified for several years while researchers tried to understand what they had found. As more bursts were detected, it became clear that they arrived from random directions in the sky, suggesting they originated outside our solar system. But their true nature remained mysterious for decades. The bursts appeared to come from enormous distances, requiring energy outputs that seemed impossible to explain. If the bursts were as distant as they appeared, they would need to release more energy in seconds than our galaxy produces in years. We now know that gamma-ray bursts come in at least two main varieties, each representing a different type of catastrophic cosmic event. Short bursts, lasting less than 2 seconds, appear to be produced by neutron star collisions. The merger of two neutron stars creates a brief black hole surrounded by a disk of extremely hot, neutron-rich matter. As this matter falls into the black hole, it gets accelerated to nearly the speed of light and focused into narrow jets. Long gamma-ray bursts, lasting from seconds to several minutes, come from the deaths of the most massive stars in events called hypernovae. These stars are so large that their cores collapse directly into black holes, bypassing the neutron star stage entirely. The collapse is so rapid and violent that it tears apart the star from the inside, creating jets of relativistic particles that punch through the stellar envelope and escape into space. In both cases, the energy is focused into narrow jets that beam outward at nearly the speed of light. This focusing effect, called relativistic beaming, concentrates the explosion's energy into cones that cover only a small fraction of the sky. Most gamma-ray bursts are probably not pointed toward Earth, making them invisible to our detectors. The ones we do see represent just the tip of the iceberg of cosmic violence. If a gamma ray burst occurred within a few thousand light years of Earth and happened to be pointed our way, it would be catastrophic for life on our planet. The initial flash would strip away much of our ozone layer within seconds, allowing deadly ultraviolet radiation to reach the surface. The gamma rays would also create nitrogen oxides in the upper atmosphere, which would further deplete ozone and create a brown smog that would persist for years. The biological effects would be devastating. The increased ultraviolet radiation would cause massive die-offs of phytoplankton, the microscopic organisms that form the base of the ocean food chain. On land, plants would be damaged or killed, leading to collapse of terrestrial ecosystems. Some scientists suspect that gamma-ray bursts might be responsible for some of the mass extinction events in Earth's history, times when up to 90% of all species disappeared from the fossil record. The Ordovician extinction, which occurred about 450 million years ago, eliminated many marine species and coincided with evidence for increased levels of ultraviolet radiation reaching Earth's surface. While other explanations are possible, a nearby gamma-ray burst could account for both the timing and the pattern of extinctions observed in the geological record. The possibility that our planet's biosphere could be sterilized by events occurring thousands of light years away puts our cosmic situation in perspective. We exist at the mercy of forces beyond our control or even our awareness. Most gamma-ray bursts are too distant to affect us, occurring in galaxies billions of light years away. But the universe is under no obligation to keep it that way, and the violent events that create these bursts are occurring somewhere in the cosmos every few seconds. This brings us to one of the most unsettling realizations about our cosmic environment. We live in what appears to be a remarkably stable period of cosmic history, but this stability is temporary and possibly quite rare. The universe we see today, filled with stars and galaxies and complex structures, represents a brief golden age in cosmic evolution, a narrow window between the chaotic violence of the early universe and the cold emptiness of the far future. In the deep past, the universe was too hot and dense for complex structures to form. For the first 380,000 years after the Big Bang, the universe was so hot that electrons couldn't stay bound to atomic nuclei. Free electrons scattered light in all directions, making the universe opaque like the inside of a star. Only when the temperature dropped below about 3,000 degrees Kelvin could stable atoms form, allowing light to travel freely through space for the first time. This transition, called recombination, marked the moment when the universe became transparent. The afterglow of this event is still visible today as the cosmic microwave background radiation, a faint glow that fills all of space. This radiation carries information about the conditions that existed when the universe was less than 400,000 years old, providing our earliest direct view of cosmic history. But even after recombination, it took hundreds of millions of years for the first stars to form. The early universe contained only hydrogen and helium, the lightest elements. Heavier elements like carbon, oxygen, and iron had to be forged in the cores of stars and scattered into space by supernova explosions before planets could form and life could begin. The universe had to age and evolve through several generations of stellar birth and death before conditions became suitable for complexity. The first stars were monsters, perhaps hundreds of times more massive than our sun. With no heavy elements to help them radiate energy efficiently, these primordial giants burned through their nuclear fuel in just a few million years before exploding as hypernovae. Their deaths scattered the first heavy elements into the cosmos, seeding future generations of stars with the materials needed to build rocky planets and, eventually, life. This cosmic enrichment process took billions of years. Each generation of stars added more heavy elements to the interstellar medium, gradually building up the chemical diversity needed for complex chemistry. Our sun is what astronomers call a population 1 star, rich in heavy elements because it formed from gas that had already been processed through multiple cycles of stellar birth and death. We exist only because countless generations of stars lived and died before us. Star formation in the universe peaked billions of years ago and has been declining ever since. The gas and dust needed to make new stars is gradually being consumed or dispersed by stellar winds and supernova explosions. The universe is slowly using up the raw materials for star formation. Most of the stars that will ever exist have already been born. In about 5 billion years, our own sun will begin its death process, swelling into a red giant and making Earth uninhabitable long before it finally burns out as a white dwarf. But this is a minor concern compared to the longer-term trends affecting the entire universe. In a few trillion years, the expansion of space will have carried distant galaxies so far away that they'll no longer be visible from the Milky Way. Our descendants, if any exist, will look up at a sky containing only our local cluster of galaxies. The local group, which includes the Milky Way, Andromeda, and several smaller galaxies, is held together by gravity and will resist the cosmic expansion. But even this local structure won't last forever. In about 4.5 billion years, Andromeda and the Milky Way will collide and merge, creating a single massive elliptical galaxy that astronomers have nicknamed Milkomeda. This collision will dramatically reshape both galaxies, flinging some stars into intergalactic space while triggering new bursts of star formation from compressed gas clouds. Eventually, even these nearby galaxies will merge together into a single, massive elliptical galaxy. Star formation will have ceased entirely by then, as all available gas will have been consumed or ejected from the galaxy. The night sky will be populated only by the slowly cooling remnants of dead stars, white dwarfs, neutron stars, and black holes. The universe will have entered what cosmologists call the degenerate era, a time when ordinary matter exists only in the form of stellar remnants. On even longer timescales, protons themselves might decay, causing all matter to gradually disappear. The theory that predicts proton decay, called grand unified theory, suggests that even the most stable particles are not truly permanent. Given enough time, every proton in the universe will eventually transform into lighter particles and energy. This process would take an almost incomprehensible amount of time, far longer than the current age of the universe multiplied by itself many times over. The only objects left after proton decay would be black holes, and even these will eventually evaporate through Hawking radiation. The final black hole, formed from the merger of all others, will take longer to disappear than the current age of the universe multiplied by itself a trillion times. When it finally evaporates, nothing will remain but a thin soup of elementary particles in an ever-expanding, ever-cooling void. This is the heat death of the universe, the ultimate fate predicted by thermodynamics when extrapolated to cosmic scales. All energy will be evenly distributed, all temperature differences will disappear, and no further work can be done. It's the closest thing to absolute ending that physics can imagine, a state of maximum entropy where nothing interesting can ever happen again. Yet even this bleak scenario contains mysteries and possibilities that might surprise us. Quantum mechanics suggests that even empty space contains virtual particles that briefly pop into existence before disappearing again. Over unimaginably vast timescales, quantum fluctuations might spontaneously create new structures, new universes, new possibilities we can't currently foresee. In a truly infinite expanse of time, even the most improbable events become inevitable. Some theoretical physicists propose that our universe might be just one bubble in an infinite foam of universes, each with different physical laws and constants. The multiverse hypothesis suggests that every possible set of physical parameters exists somewhere, creating a vast ensemble of realities with different properties. In some universes, the strong nuclear force is weaker, preventing the formation of complex atomic nuclei. In others, gravity is stronger, causing stars to burn out quickly and black holes to dominate. The constants that govern our universe appear to be fine-tuned for the existence of complex structures, change the strength of gravity slightly, and stars either burn out too quickly or never ignite at all, alter the strong nuclear force, and atomic nuclei become unstable. adjust the balance between matter and dark energy, and galaxies never form. The fact that all these parameters happen to allow for the existence of stars, planets, and ultimately life seems almost miraculous. Some scientists argue that this apparent fine-tuning is evidence for design, though they rarely specify who or what might have done the designing. The anthropic principle suggests a different explanation. We observe a universe suitable for our existence because we couldn't exist in any other kind. It's a selection effect, like asking why fish find themselves in water rather than on dry land. Others suggest that we live in a multiverse where all possible values of physical constants exist somewhere, and we necessarily find ourselves in a region where the values allow for observers like us. This infinite ensemble of universes would contain every possible variation of physical law, from universes where chemistry never develops to universes where new forms of complexity emerge that we can't imagine. But there's a third possibility that's perhaps most unsettling of all. Maybe the universe isn't fine-tuned for life as we know it. Maybe life as we understand it is just one possible way that complex information processing can emerge from the basic laws of physics. In universes with different constants, entirely different forms of organization and complexity might arise, forms so alien to our experience that we wouldn't recognize them as life at all. We have exactly one example of a universe to study, our own. This makes it impossible to know whether the conditions we observe are typical or extraordinary. Are we living in a cosmic paradise perfectly suited for biological evolution, or are we simply making do with whatever physical laws happen to exist, finding ways to thrive under conditions that might seem hostile to other forms of potential existence? The question becomes even more complex when we consider the possibility that the physical laws themselves might evolve over time. Some theories suggest that what we call constants might actually be variables that change as the universe ages. The strength of gravity, the speed of light, the masses of fundamental particles all might have been different in the past and might change again in the future. If the laws of physics are mutable, then the fine-tuning problem disappears entirely. The universe doesn't need to start with exactly the right constants to allow for complexity. Instead, the constants themselves might evolve toward values that promote the emergence of structure and organization. The universe might be self-tuning, gradually adjusting its own parameters to maximize complexity and information processing. This idea connects to deeper questions about the relationship between physical laws and information. Some physicists propose that reality is fundamentally computational, that the universe is essentially running a vast program whose output is everything we experience. In this view, particles and forces are subroutines, and what we call physical laws are the algorithms that govern how information is processed. The computational universe hypothesis suggests that space and time themselves might be emergent properties of information processing rather than fundamental aspects of reality. Just as a computer can simulate complex three-dimensional worlds using simple binary operations, the universe might create the appearance of continuous space and time through discrete computational steps occurring at scales far below what we can observe. If the universe is indeed computational in nature, then questions about its ultimate fate take on new meaning. Computer programs can halt, reaching a final state where no further computation is possible. But they can also run indefinitely, generating infinite complexity from finite rules. Perhaps consciousness and intelligence aren't accidents that briefly flicker in a dying universe, but fundamental features of reality that will find new ways to manifest themselves regardless of changing physical conditions. This brings us to one of the most profound questions we can ask about our cosmic situation. Are we alone? The observable universe contains at least 2 trillion galaxies, each containing hundreds of billions of stars. Many of these stars have planets, and some of those planets exist in the habitable zones where liquid water can exist on their surfaces. The sheer scale of the universe seems to make the existence of other life almost inevitable. The numbers appear overwhelmingly in favor of extraterrestrial life. Our galaxy alone contains over 100 billion stars, and recent surveys suggest that most of these have planetary systems. If even a tiny fraction of planets develop life, and a tiny fraction of those develop intelligence, the galaxy should be teeming with civilizations. Yet despite decades of searching with increasingly sophisticated instruments, we have found no definitive evidence for life beyond Earth. This absence of evidence has been formalized as the Fermi Paradox, named after physicist Enrico Fermi, who reportedly asked his colleagues during lunch one day, "Where is everybody?" The question encapsulates one of the most puzzling aspects of our cosmic situation. If life is common, as the numbers suggest it should be, why haven't we encountered it? The paradox has many possible solutions, each more unsettling than the last. Perhaps life is far rarer than we think, requiring such an unlikely chain of coincidences that Earth might be unique in the observable universe. The emergence of life might require not just the right chemical conditions, but also the right planetary environment, the right stellar system, the right galactic location, and perhaps even the right cosmic timing. Earth has benefited from numerous apparent coincidences that have maintained stable conditions for billions of years. Our large moon stabilizes the planet's rotational axis, preventing extreme climate swings that might disrupt evolution. Jupiter acts as a gravitational shield, deflecting many comets and asteroids that might otherwise impact Earth. Our position in the galaxy keeps us away from the radiation-intense central regions, while providing access to the heavy elements needed for rocky planets. Perhaps intelligence is common but consistently self-destructs before it can spread to the stars. The transition from planetary to spacefaring civilization might represent a dangerous bottleneck where most species eliminate themselves through war, environmental destruction, or other self-inflicted catastrophes. The same intelligence that allows for technology and space travel might inevitably lead to weapons and behaviors that threaten survival. Human civilization has existed for only a few thousand years, and we've already developed the capability to destroy ourselves through nuclear weapons, climate change, or biological warfare. Perhaps every intelligent species faces similar challenges, and most fail to navigate them successfully. We might be living during the brief window when our species has the power to destroy itself, but hasn't yet learned the wisdom to avoid doing so. Alternatively, perhaps advanced civilizations exist, but choose to remain hidden from us. They might follow ethical principles that prohibit interference with developing species, allowing younger civilizations to evolve naturally without outside influence. We might exist in something like a cosmic nature preserve, protected and studied, but kept isolated from the larger galactic community until we reach some threshold of maturity or technological capability. Even more disturbing is the possibility that we are observed but considered unworthy of contact. Perhaps there are standards for galactic citizenship that we haven't yet met. Our violence, environmental destruction, and inability to cooperate on a planetary scale might mark us as too primitive or dangerous for inclusion in an advanced civilization. Or perhaps they're already here, operating on scales of time and space so vast that we don't recognize their presence. A civilization millions of years more advanced than us might manipulate matter and energy in ways that appear to us as natural phenomena. They might engineer stars to extend their lifetimes, move planets to more favorable orbits, or reshape entire galaxies according to their needs. We would interpret their actions as astronomy rather than technology. The absence of obvious alien signals might not mean we're alone. It might mean that sufficiently advanced intelligence doesn't communicate in ways we can recognize or intercept. They might use quantum entanglement for instantaneous communication across vast distances, or encode their messages in gravitational waves, or embed information in the cosmic microwave background radiation itself. Our radio searches might be like trying to detect internet traffic by listening for smoke signals. Even more sobering is the possibility that intelligence, once it reaches a certain level of sophistication, tends to turn inward rather than outward. Perhaps advanced civilizations discover that the most interesting explorations lie in the realms of consciousness, mathematics, or virtual reality rather than in physical space? Why build starships when you can create entire universes inside computer simulations? Why colonize planets when you can upload minds to substrates that don't require planetary resources? The implications of alien contact, should it ever occur, would reshape human understanding of our place in the universe more dramatically than any scientific discovery in history. But the implications of confirmed solitude might be even more profound. To discover that consciousness and intelligence emerged only once in the observable universe would make humanity unimaginably precious and unimaginably responsible. If we are alone, then we are the universe's only chance to understand itself, at least in this region of space and time. Every human mind that develops scientific understanding, every moment of artistic creation, every act of compassion or moral insight becomes cosmically significant. The death of our species would mean the end of the universe's capacity for self-awareness, at least until some other form of intelligence evolves elsewhere. But even if we're not alone, even if intelligence is common throughout the cosmos, each conscious mind remains extraordinary. The fact that the universe has evolved structures complex enough to contemplate their own existence is perhaps the most remarkable thing that has ever happened. Matter has become aware of itself. Temporary arrangements of atoms have developed the ability to ponder infinity, and localized patterns of information processing have learned to decode the deepest secrets of cosmic architecture. Your brain contains approximately 86 billion neurons, each connected to thousands of others, through a network more complex than the visible structure of the entire universe. The electrochemical processes that generate your thoughts involve quantum mechanics at the molecular level, classical physics at the cellular level, and emergent phenomena at the systems level. Your consciousness emerges from the interaction of billions of individual components, none of which is itself conscious. How this happens remains one of the greatest mysteries in science. We can map brain activity with increasing precision, trace neural pathways, and correlate mental states with physical processes, but the actual mechanism by which subjective experience arises from objective matter is still unknown. The hard problem of consciousness, as philosophers call it, concerns not just how the brain processes information, but how and why there is any internal experience at all. Some researchers think consciousness is an emergent property of sufficiently complex information processing systems. In this view, any system that processes information in sufficiently sophisticated ways will eventually develop subjective experience. Artificial intelligences, once they become complex enough, might become genuinely conscious rather than merely simulating consciousness. Others believe consciousness requires specific biological processes that evolved over millions of years of natural selection. The particular way that neurons integrate information, the role of neurotransmitters and glial cells, the quantum effects that might occur in microtubules within brain cells, all these factors might be necessary for genuine awareness. In this view, consciousness might be impossible to replicate in non-biological systems. Still others argue that consciousness is a fundamental feature of reality, present at some level in all matter. This panpsychist view suggests that electrons and photons have primitive forms of experience, and that complex consciousness emerges when these simple experiences are integrated in sophisticated ways. Your mind might be made up of billions of tiny conscious entities working together to create unified awareness. The question matters because it determines whether minds like yours could eventually be replicated in other substrates or uploaded to artificial systems. If consciousness is purely computational, then the pattern of information processing that constitutes your mind might survive the death of your biological brain. If consciousness requires specific biological processes, then your subjective experience might be permanently tied to your organic neural network. But regardless of its ultimate nature, your consciousness represents something precious and possibly unique in the cosmic order. You exist during the brief golden age when stars shine and complex chemistry is possible. You live on a planet where evolution had enough time to create nervous systems capable of understanding their cosmic environment You belong to a species that has learned to see across billions of light years and back billions of years in time. The universe you inhabit is not the tame, predictable cosmos described in elementary textbooks. It's a place where space and time can be bent, where the majority of all existence is invisible, where black holes can erase information from reality. It's a place where neutron stars pack the mass of the sun into the space of a city, where gamma-ray bursts can sterilize entire regions of the galaxy, where quantum mechanics allows particles to exist in multiple states simultaneously until they are observed. Most of cosmic history occurred without any witness to observe or understand it. Galaxies formed and evolved. Stars were born and died. Black holes grew and evaporated. Supernovae scattered heavy elements through space, all without any intelligence to note their passing or comprehend their significance. The universe spent nearly 14 billion years preparing for the emergence of minds capable of asking questions about their origins and fate, whether humanity represents the first flowering of cosmic intelligence or merely one example among countless others scattered throughout space and time. We are the universe in the process of waking up to itself. Every scientific discovery extends the reach of cosmic self-awareness. Every moment of wonder or understanding represents matter transcending its apparent limitations to contemplate its own nature. The story you learned in school was necessarily simplified, edited for minds not yet ready to grapple with infinite spaces and fundamental uncertainties. The universe was presented as a collection of objects, planets, stars, galaxies, rather than as a dynamic system of interacting fields and forces operating on scales that dwarf human comprehension. You were taught that time flows uniformly and that space is empty except where matter occupies it, useful approximations that bear little resemblance to the strange reality revealed by careful observation. But now you know something closer to the truth. The universe is vast beyond imagining, ancient beyond comprehension, and strange beyond belief. Dark matter and dark energy dominate reality in ways we're only beginning to understand. Black holes warp space-time so severely that the normal rules of physics break down entirely. Neutron stars create matter so dense that a teaspoon would weigh more than a mountain. Gamma-ray bursts release more energy in seconds than our sun will produce in its entire lifetime. Stars exist that shouldn't be able to form according to our best theories. Some objects appear older than the universe itself. Space is expanding at an accelerating rate, driven by a mysterious energy that makes up more than 2/3 of everything that exists. Quantum mechanics suggests that reality splits into multiple branches at every moment, creating an infinite ensemble of parallel universes where every possibility plays out. And in the midst of all this cosmic strangeness, on a small, rocky planet orbiting an ordinary star in an unremarkable galaxy, matter has organized itself into patterns complex enough to contemplate the very questions that have driven this exploration. Carbon atoms forged in the cores of dying stars have assembled into neural networks capable of understanding stellar nucleosynthesis. Hydrogen atoms created in the Big Bang have learned to calculate the age and size of the universe that gave them birth. You are the universe thinking about itself. Your consciousness represents the cosmos becoming aware of its own existence, structure, and evolution. Every thought you have about the nature of reality is the universe exploring its own depths. Every moment of scientific understanding is matter transcending its apparent limitations to comprehend the forces and processes that shaped it. That makes you, quite literally, one of the most remarkable things that has ever happened. Not because you are separate from the universe, but because you are the universe becoming conscious of itself. You embody 13.8 billion years of cosmic evolution, from the first moments after the Big Bang through the formation of galaxies and stars and planets, through the emergence of life and the development of nervous systems complex enough to ponder their origins. The education you received in school taught you to function in human society, to understand the immediate world around you, to develop skills useful for terrestrial life. That education was essential and valuable. But the real universe, the complete picture of existence, is far more magnificent and terrifying than any classroom could convey. Space is not empty, but filled with invisible matter and energy that shape the cosmic architecture. Time is not uniform, but flexible, slowing down near massive objects and speeding up in their absence. Matter and energy are interchangeable. Space and time are joined together, and the act of observation can change the reality being observed. The comfortable certainties of everyday experience dissolve when confronted with cosmic scales and quantum phenomena. Yet somehow, from this strange and beautiful chaos, patterns emerge that are stable enough to support the existence of stars and planets, complex chemistry and biological evolution, nervous systems and consciousness. You now know something of what they didn't teach you about the universe. The question is, what you'll do with that knowledge, how it will change your perspective on your brief time as a conscious observer in an ancient and infinite cosmos. Will it make you feel insignificant, a tiny speck in a vast, uncaring universe? Or will it help you recognize yourself as part of something magnificent, a temporary arrangement of matter that has achieved the extraordinary feat of understanding its place in the cosmic order? The universe has waited 13.8 billion years for you to understand these things. Stars lived and died to create the elements in your body. Galaxies formed and evolved to provide the stable environment in which planetary systems could develop. The laws of physics conspired to allow the emergence of complexity and consciousness. What happens next in this cosmic story is, at least in part, up to you. But before we conclude this journey through cosmic reality, let's dive deeper into some of the most mind-bending facts that make our universe even stranger than we've already explored. The details matter because they reveal just how precarious and extraordinary our existence truly is. Consider the cosmic microwave background radiation that we mentioned earlier. This afterglow of the Big Bang isn't just a uniform glow-filling space. It contains tiny fluctuations, variations in temperature of just a few millionths of a degree. These minuscule differences represent the seeds from which all cosmic structure grew. Regions that were slightly denser than average eventually became the sites where galaxies formed. Areas that were slightly less dense became the vast, empty spaces, called cosmic voids, that separate galaxy clusters today. The precision required for this process to work is staggering. If the initial density fluctuations had been much larger, matter would have collapsed into black holes before stars could form. If they had been much smaller, gravity would never have been able to pull matter together into galaxies at all. The universe would have remained a thin, uniform soup of particles forever. The fact that the fluctuations were exactly the right size to allow for cosmic structure represents a level of fine-tuning that boggles the mind. These temperature variations in the cosmic microwave background also tell us something profound about the geometry of space itself. When we map these fluctuations across the entire sky, we find that they follow patterns that reveal the shape of the universe. The size and distribution of hot and cold spots depends on whether space is curved like the surface of a sphere, curved like a saddle, or perfectly flat like an infinite sheet of paper. The measurements show that our universe is flat to within a fraction of a percent. This flatness extends as far as we can see in every direction, suggesting that space continues with the same geometry beyond the observable horizon. A flat universe has profound implications. It means that parallel lines never meet, that the angles of triangles always add up to 180 degrees, and that the universe will expand forever rather than eventually collapsing back on itself. But this flatness creates what cosmologists call the flatness problem. In the early universe, the geometry of space was determined by a delicate balance between the expansion rate and the total density of matter and energy. For the universe to be flat today, this balance had to be precise to more than 50 decimal places in the first moments after the Big Bang. Any significant deviation would have led to a universe that either collapsed immediately or expanded so rapidly that no structures could ever form. The solution to this problem involves a period called cosmic inflation, when the universe expanded exponentially during the first tiny fraction of a second after its birth. in less than 10 to the negative 30 seconds, a region smaller than a proton inflated to the size of a grapefruit. This incredible expansion stretched out any initial curvature, making the universe appear flat from our perspective, just as the surface of a balloon appears flat to an ant walking on it. Inflation also explains why the cosmic microwave background radiation has almost exactly the same temperature in all directions. Without inflation, opposite sides of the sky would represent regions that were never in contact with each other, yet they show the same temperature to within a few parts per million. Inflation shows us that these apparently disconnected regions were actually in close contact before the exponential expansion separated them. The physics of inflation pushes our understanding to its limits. The process requires a special kind of energy field called an inflaton field that creates a repulsive gravitational effect. Unlike normal matter, which slows down cosmic expansion through its gravitational attraction, the inflaton field accelerates expansion. This field had to have just the right properties to turn on suddenly, drive rapid expansion for exactly the right amount of time, then decay into the ordinary matter and energy we see today. The energy scales involved in inflation are mind-numbing. During the inflationary epoch, the energy density of the inflaton field was about 10 to the 80 times greater than the density of water. To put this in perspective, if you took all the energy in a cubic centimeter of space during inflation and converted it to mass, you would get about 10 to the 50 kilograms, roughly the mass of 10 to the 20 suns, packed into a volume smaller than a sugar cube. When inflation ended, this enormous energy had to be converted into the particles and radiation that filled the early universe. The process, called reheating, created temperatures of about 10 to the 28th power degrees, hot enough to create and destroy the most massive particles allowed by physics. At these temperatures, the fundamental forces that govern nature behaved very differently than they do today. In our current cool universe, we observe four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But at the incredibly high temperatures that existed during reheating, these forces were unified into a single superforce. As the universe cooled, this unified force underwent a series of phase transitions, similar to how water vapor condenses into liquid and then freezes into ice, separating into the distinct forces we observe today. The first phase transition occurred when gravity separated from the other forces at a temperature of about 10 to the 32nd degrees. This happened about 10 to the minus 43 seconds after the Big Bang, a moment known as the Planck time. Before this instant, our current theories of physics break down completely. We don't know what happened during the first 10 to the minus 43 seconds of cosmic history because we lack a theory that can describe gravity and quantum mechanics together. The next phase transition occurred when the strong nuclear force separated from the electroweak force at a temperature of about 10 to the 28th degrees. This happened about 10 to the minus 36 seconds after the Big Bang and may have been the event that triggered cosmic inflation. The energy released during this phase transition could have powered the exponential expansion that shaped the universe's large-scale structure. The final phase transition occurred much later, when the electromagnetic and weak nuclear forces separated at a temperature of about 10 to the 15th degrees. This happened about 10 to the minus 12 seconds after the Big Bang, when the universe was already old by the standards of particle physics. After this point, the four fundamental forces had taken on their modern forms and strengths. These phase transitions didn't occur uniformly throughout space. Different regions underwent the transitions at slightly different times and in slightly different ways, creating defects in the fabric of space-time itself. These cosmic defects include monopoles, strings, domain walls, and textures. Exotic objects that might still exist in the universe today, though they would be extremely rare. Cosmic strings, if they exist, would be one-dimensional objects thinner than a proton, but potentially stretching across the entire observable universe. A piece of cosmic string just 1 meter long would have a mass greater than Mount Everest. These strings would be moving at nearly the speed of light, and their gravitational effects would create distinctive patterns in the cosmic microwave background radiation. Domain walls would be two-dimensional sheets separating regions of space with different properties. If domain walls formed during the early universe and survived to the present day, they would eventually come to dominate the energy density of the cosmos, leading to a very different evolutionary history than what we observe. The fact that we don't see evidence for domain walls tells us something important about the nature of the phase transitions that occurred in the early universe. The search for these cosmic relics continues, using increasingly sensitive instruments to look for their subtle effects on the cosmic microwave background radiation and the large-scale distribution of galaxies. Finding evidence for cosmic strings or other topological defects would provide direct confirmation of our theories about the early universe and the fundamental nature of physical law. But perhaps the most profound implication of our current understanding involves the concept of eternal inflation. Many models suggest that inflation, once it begins, can never completely stop everywhere. While inflation ended in our observable universe, it might continue forever in other regions, constantly creating new universes with different properties. In the eternal inflation scenario, our Big Bang was not the beginning of everything, but just one event in an infinitely ongoing process of universe creation. Space is filled with an infinite number of bubble universes, each with its own Big Bang, its own physical laws, and its own evolutionary history. Most of these universes would be sterile, lacking the right conditions for stars, planets, or life. But in an infinite ensemble, every possible combination of physical laws would exist somewhere. This multiverse concept pushes the boundaries of science into philosophy. If eternal inflation is correct, then our universe, with all its apparent fine-tuning for life, is just one random sample from an infinite collection. The anthropic principle would explain why we find ourselves in a life-friendly universe. We couldn't exist anywhere else. But this explanation comes at the cost of making our universe seem less special, just one unremarkable bubble in an infinite cosmic foam. The implications extend to questions about the nature of physical law itself. In our universe, the electron has a specific mass, the speed of light has a specific value, and the strength of gravity follows a specific mathematical relationship. We typically think of these as fundamental constants, unchanging features of reality. But in the multiverse scenario, these constants would be variables that take on different values in different bubble universes. Some physicists argue that this makes the multiverse hypothesis unscientific, since it seems to explain everything by explaining nothing. If every possible universe exists somewhere, then no particular observation can be used to test the theory. Others contend that the multiverse is a natural consequence of our best theories, and that we should follow the mathematics wherever it leads, even into realms that seem to defy common sense. The debate touches on fundamental questions about the nature of scientific explanation. Should we accept theories that make our universe seem typical rather than special? Can we ever have evidence for the existence of other universes that are causally disconnected from our own? How do we distinguish between legitimate scientific speculation and unfalsifiable metaphysics? These questions become even more complex when we consider the role of quantum mechanics in cosmic evolution. Quantum theory suggests that the wave function of the universe, which describes all possible quantum states, never collapses into a single definite reality. Instead, every quantum measurement splits the universe into multiple branches, each representing a different possible outcome. The many worlds interpretation of quantum mechanics implies that you are constantly branching into multiple versions of yourself. Every time a quantum measurement occurs anywhere in the universe, reality splits into parallel branches. In some branches, you decided to have coffee this morning instead of tea. In others, you chose a different route to work. In still others, historical events unfolded in completely different ways. If many worlds is correct, then the number of parallel universes containing versions of you increases exponentially with time. Most of these parallel selves differ from you in trivial ways, but some live in worlds where the course of history was dramatically altered by different quantum outcomes. There are branches where the dinosaurs never went extinct, where human civilization developed differently, where the laws of physics themselves might be subtly different due to different quantum boundary conditions in the early universe. The total number of parallel branches would be truly infinite, growing without bound as quantum measurements continue to occur. Every possible quantum history would be realized somewhere in this vast ensemble of realities. From this perspective, the multiverse isn't just a possibility suggested by inflation theory, but an inevitable consequence of quantum mechanics itself. But even setting aside these speculative scenarios, the universe we can actually observe contains wonders that challenge our deepest assumptions about the nature of reality. Consider the phenomenon of quantum entanglement, where particles can be correlated in ways that seem to violate our intuitive understanding of space and time. When two particles become entangled, measuring the properties of one particle instantly determines the properties of the other, regardless of how far apart they are. Einstein famously called this spooky action at a distance because it seemed to require instantaneous communication across arbitrary distances. He believed that quantum mechanics must be incomplete, that there must be hidden variables that predetermine the outcomes of measurements, but experiments have repeatedly confirmed that entanglement is real and that there are no hidden variables that could explain the correlations. When particles are entangled, they genuinely seem to form a single quantum system that transcends ordinary notions of locality. The measurement of one particle really does instantly affect its entangled partner, even if they are separated by billions of light years. This doesn't allow for faster than light communication because the results of quantum measurements appear random to any individual observer. You can't use entanglement to send messages because you have no control over what results your measurements will produce. But the correlations between distant measurements are stronger than classical physics allows, suggesting that reality at its deepest level is fundamentally non-local. The implications extend far beyond laboratory experiments. If the universe began in a quantum state, as suggested by inflationary cosmology, then distant regions of space might still be entangled with each other. The cosmic microwave background radiation coming from opposite sides of the sky might be correlated in subtle ways that reflect quantum entanglement established during inflation. Some theories suggest that entanglement might play a role in the structure of space-time itself. In these approaches, the geometry of space emerges from patterns of quantum entanglement between fundamental degrees of freedom. Distance and time might not be basic features of reality, but rather emergent properties of more fundamental quantum correlations. The holographic principle, developed from studies of black hole physics, suggests that all the information contained in any volume of space can be encoded on the surface that bounds that volume. This means that three-dimensional reality might be like a hologram, with all the information needed to describe the interior encoded on a two-dimensional boundary. If the holographic principle is correct, then the three-dimensional space you think you inhabit might be an illusion. The fundamental reality might be two-dimensional, with the appearance of a third dimension emerging from complex patterns of information processing on the holographic boundary. Your brain, your thoughts, your entire experience of three-dimensional existence might be encoded in a two-dimensional quantum field. These ideas push the boundaries of what we can meaningfully say about the nature of reality. They suggest that space, time, matter, and energy might all be emergent phenomena arising from more fundamental quantum information processes. The universe might be better understood as a vast quantum computer than as a collection of particles moving through space. But even our most exotic theories must confront the basic observational facts about the cosmos. One of the most striking features of our universe is how remarkably uniform it appears on the largest scales, despite being highly structured on smaller scales. When we look at the distribution of galaxies across billions of light years, we find that matter is spread out in a vast web-like pattern, with dense filaments separated by enormous voids. This cosmic web structure reflects the initial density fluctuations that existed shortly after the Big Bang, amplified by billions of years of gravitational evolution. Computer simulations can reproduce this large-scale structure with remarkable accuracy, showing how tiny quantum fluctuations during inflation grew into the galaxy clusters and cosmic voids we observe today. The simulations reveal that normal matter, the stuff that makes up stars and planets, plays a relatively minor role in determining large-scale structure. The dominant component is dark matter, which forms the scaffolding upon which normal matter assembles into galaxies. Without dark matter, the universe would look completely different, with much smaller and more diffuse structures that could never have produced the dense environments needed for star formation and planetary systems. The nature of dark matter remains one of the deepest mysteries in cosmology. We know it exists because of its gravitational effects, but we have never detected dark matter particles directly, despite decades of increasingly sophisticated experiments. The leading candidates are weakly interacting massive particles, or WIMPs, that would interact with normal matter only through gravity and the weak nuclear force. Underground detectors filled with liquid xenon or other target materials wait patiently for dark matter particles to collide with atomic nuclei, producing tiny flashes of light or heat that could be detected with sensitive instruments. But year after year, these experiments see nothing definitive, placing ever more stringent limits on the properties that dark matter particles could have. The failure to detect dark matter particles has led some physicists to propose more exotic alternatives. Perhaps dark matter consists of axions, hypothetical particles that are much lighter than WIMPs, but far more numerous. Axions would interact so weakly with normal matter that they could pass through the entire Earth without ever colliding with a single atom. Another possibility is that dark matter particles interact with each other through forces that have nothing to do with the familiar particles and fields of the Standard Model. Dark matter might exist in its own hidden sector of physics, with its own forces and interactions that remain completely invisible to our instruments. From our perspective, dark matter would appear to interact only gravitationally, but within the dark sector, there might be dark chemistry, dark binding energies, even dark complexity. Some theories suggest that dark matter might consist of primordial black holes formed in the early universe. These would be very different from the stellar mass black holes created by collapsing stars. Primordial black holes could have a wide range of masses, from microscopic objects lighter than a paperclip to monsters more massive than entire star clusters. If primordial black holes make up a significant fraction of dark matter, they would occasionally pass through our solar system, creating subtle gravitational effects that might be detectable with precise measurements of planetary orbits or spacecraft trajectories. They might also create distinctive patterns in the cosmic microwave background radiation as they move through space. The search for dark matter has become one of the most intensive efforts in modern physics, involving experiments deep underground, in space, and in particle accelerators around the world. The Large Hadron Collider has searched for signs of dark matter particles created in high-energy collisions, while space-based telescopes look for the gamma rays that might be produced when dark matter particles annihilate each other. But perhaps the most profound mystery involves dark energy, the mysterious force that is accelerating the expansion of the universe. Unlike dark matter, which behaves like ordinary matter except for its invisibility, dark energy appears to have properties unlike anything else we know about. The energy density of dark energy appears to be constant throughout space and time. As the universe expands and the density of matter decreases, the density of dark energy remains the same. This means that dark energy becomes increasingly dominant as the universe ages, eventually overwhelming the gravitational effects of all matter, both normal and dark. The constancy of dark energy density creates what physicists call the cosmological constant problem. If dark energy is truly a property of empty space, then its energy density should be related to the quantum fluctuations that occur in vacuum. But when physicists calculate what this energy density should be based on quantum field theory, they get a result that is larger than the observed value by a factor of 10 to the power of 120, making it perhaps the worst prediction in the history of science. This enormous discrepancy suggests that our understanding of vacuum energy is fundamentally flawed, or that dark energy is not related to vacuum fluctuations at all. Some theories propose that dark energy is a dynamic field, similar to the inflaton field that drove cosmic inflation, that changes its properties over time. In these models, the acceleration of cosmic expansion might be temporary, eventually giving way to deceleration or even contraction. Other theories suggest that our observations of cosmic acceleration are not due to dark energy at all, but rather to modifications of gravity on cosmic scales. These modified gravity theories attempt to explain the apparent acceleration without invoking mysterious new forms of energy, but they face significant challenges in matching all the available observational data. The ultimate fate of the universe depends critically on the nature of dark energy. If dark energy remains constant, the universe will continue accelerating forever, eventually entering a phase called the Big Rip, where the expansion becomes so rapid that it tears apart galaxies, stars, planets, and eventually atoms themselves. If dark energy decays over time, the universe might eventually stop accelerating and enter a phase of deceleration that could lead to a big crunch. Some models suggest that dark energy might even change sign, transforming from a repulsive force into an attractive one. This would cause the universe to collapse much more rapidly than ordinary gravity alone could accomplish, creating a cosmic catastrophe that would end everything in a finite time. The precision with which we can measure cosmic acceleration continues to improve as new generations of telescopes come online. Projects like the Dark Energy Survey and the upcoming Vera Rubin Observatory will observe millions of distant galaxies and supernovae, mapping the expansion history of the universe with unprecedented accuracy. These observations will help determine whether dark energy is truly constant or whether it changes over time in ways that could reveal its fundamental nature. They will also search for subtle effects that could distinguish between different models of cosmic acceleration, potentially resolving one of the deepest mysteries in modern cosmology. But even as we struggle to understand dark energy, we continue to discover new phenomena that challenge our understanding of cosmic evolution. Recent observations have revealed that the rate of cosmic expansion measured using nearby objects differs slightly from the rate inferred from the cosmic microwave background radiation. This discrepancy, known as the Hubble tension, might indicate that our standard model of cosmology is incomplete. Perhaps there are additional components of dark energy that were important in the past but are negligible today. Perhaps the properties of dark matter are more complex than we assumed. Or perhaps our understanding of stellar evolution, which is used to calibrate distance measurements, needs revision. The Hubble tension has persisted despite increasingly precise measurements, suggesting that it might represent a genuine crisis in cosmology rather than a systematic error. If confirmed, it could point toward new physics beyond the standard model, potentially revolutionizing our understanding of cosmic evolution. These ongoing mysteries remind us that despite all our progress in understanding the universe, we are still far from a complete picture of cosmic reality. The universe continues to surprise us with phenomena that don't fit neatly into our theoretical frameworks, forcing us to revise and extend our understanding of fundamental physics. Perhaps most remarkably, we are able to contemplate these mysteries at all. The fact that conscious observers have emerged in this universe and developed the capability to study their cosmic environment represents an extraordinary development in the long history of cosmic evolution. From quantum fluctuations in the early universe to the complex neural networks that generate thoughts and consciousness, the chain of cause and effect that led to your ability to understand these concepts spans the entire history of the cosmos. You are literally made of star stuff, as Carl Sagan famously noted: the carbon in your muscles, the calcium in your bones, the iron in your blood, all were forged in the nuclear furnaces of ancient stars and scattered into space by supernova explosions. Your body contains elements that were created in some of the most violent events the universe has ever produced. But beyond this poetic connection, you represent something far more profound. You are the universe becoming conscious of itself, a temporary arrangement of matter and energy that has developed the extraordinary capability to understand the physical laws that govern cosmic evolution. Through your thoughts, the universe contemplates its own nature, origin, and fate. The universe has waited 13.8 billion years for this moment of self-awareness. It has evolved through phases of incredible violence and creativity, from the quantum foam of the Planck epoch through cosmic inflation, primordial nucleosynthesis, recombination, the formation of the first stars, the assembly of galaxies, the forging of heavy elements, the formation of planetary systems, the emergence of life, and the evolution of consciousness. Every step in this cosmic story was necessary for your existence. Without cosmic inflation, the universe would have collapsed or expanded too rapidly for structures to form. Without dark matter, galaxies would never have assembled. Without stellar nucleosynthesis, there would be no carbon, oxygen, or other elements needed for complex chemistry. Without supernova explosions, these elements would have remained trapped inside stellar cores. Without the formation of second-generation stars, there would be no rocky planets. Without the protection of magnetic fields and atmospheres, there would be no stable environments for life to evolve. The chain of cosmic evolution that led to consciousness is not just improbable. It required the coordination of physical processes operating on scales from subatomic to cosmic, over time periods from nanoseconds to billions of years. Yet here you are, contemplating these very processes, understanding your place in the cosmic story, and wondering about the ultimate meaning and purpose of existence itself. What happens next in this cosmic story remains to be written. Will consciousness spread throughout the universe, transforming dead matter into living systems that can understand and appreciate the beauty of cosmic architecture? Will intelligence find ways to transcend the physical limitations that seem to doom the universe to heat death? Will conscious observers discover new physics that allows for forms of existence we cannot currently imagine? These questions remain open, their answers depending partly on choices yet to be made by conscious beings like yourself. The universe has evolved the capacity for self-awareness, but what it does with that capacity is still being determined. You are not just a passive observer of cosmic evolution. You are an active participant in the next phase of the universe's development. The story they didn't teach you in school is not just about what the universe is, but about what it might become. And in that ongoing story, your consciousness, your understanding, your choices, and your actions all play a role in determining how the cosmic narrative unfolds. The universe is not just something you observe. It is something you are helping to create through the very act of understanding it. Without supernova explosions, these elements would have remained trapped inside stellar cores. Without the formation of second-generation stars, there would be no rocky planets. Without the protection of magnetic fields and atmospheres, there would be no stable environments for life to evolve. The chain of cosmic evolution that led to consciousness is not just improbable, it required the coordination of physical processes operating on scales from subatomic to cosmic, over time periods from nanoseconds to billions of years. Yet here you are, contemplating these very processes, understanding your place in the cosmic story, and wondering about the ultimate meaning and purpose of existence itself. What happens next in this cosmic story remains to be written. Will consciousness spread throughout the universe, transforming dead matter into living systems that can understand and appreciate the beauty of cosmic architecture? Will intelligence find ways to transcend the physical limitations that seem to doom the universe to heat death? Will conscious observers discover new physics that allows for forms of existence we cannot currently imagine? These questions remain open, their answers depending partly on choices yet to be made by conscious beings like yourself. The universe has evolved the capacity for self-awareness, but what it does with that capacity is still being determined. You are not just a passive observer of cosmic evolution, you are an active participant in the next phase of the universe's development. The story they didn't teach you in school is not just about what the universe is, but about what it might become. And in that ongoing story, your consciousness, your understanding, your choices, and your actions all play a role in determining how the cosmic narrative unfolds. The universe is not just something you observe, it is something you are helping to create through the very act of understanding it. That realization might be the most profound fact of all, but there's still more to this cosmic story that deserves our attention. Details that reveal just how extraordinary and precarious our existence truly is. Let's delve deeper into some of the most remarkable processes that had to unfold with perfect precision for you to be here contemplating these questions. Consider the process of stellar nucleosynthesis, the cosmic alchemy that creates the elements essential for life. When the first stars ignited in the primordial universe, they contained only hydrogen and helium. Everything heavier had to be built from scratch through nuclear fusion reactions occurring at temperatures of millions of degrees in stellar cores. The process begins with the proton-proton chain, where hydrogen nuclei fuse to form helium. This sounds straightforward, but it requires overcoming the enormous electrical repulsion between positively charged protons. At the temperatures found in stellar cores, only about one collision in 10 to the 28th power has enough energy to overcome this barrier and result in fusion. The Sun converts about 600 million tons of hydrogen into helium every second, yet this represents the fusion of only an infinitesimally small fraction of the proton collisions occurring in its core. Once a star has converted enough hydrogen to helium in its core, the balance between gravity and radiation pressure shifts. The core contracts and heats up until it reaches the 100 million degree temperature needed for helium fusion. 3 helium nuclei combine in a process called the triple alpha reaction to form carbon. This reaction is extraordinarily sensitive to the fundamental constants of physics. The triple alpha process requires what physicists call a resonance, discovered by Fred Hoyle in the 1950s. Without this resonance, the reaction would be too slow to produce significant amounts of carbon during a star's lifetime, but the resonance exists at exactly the right energy level to make carbon production efficient. If the strong nuclear force were just 5% weaker, no carbon would be produced. If it were 5% stronger, all the carbon would be converted to oxygen, leaving none for the complex chemistry that life requires. This fine-tuning of the triple alpha reaction represents one of the most striking examples of how the fundamental constants appear to be adjusted for the production of complexity. Hoyle himself was so impressed by this apparent design that he famously remarked that it looked like someone had been monkeying with the laws of physics. The alternative explanation that we exist only because we happen to live in a universe where the constants have life-friendly values requires accepting that countless other universes exist with different sterile parameter values. The nucleosynthesis process continues in the most massive stars, building increasingly heavy elements through successive fusion reactions. Silicon burning creates iron, nickel, and cobalt, but iron represents a barrier that fusion cannot cross. Iron nuclei are the most tightly bound of all atomic nuclei, meaning that fusing them together actually absorbs energy rather than releasing it. When a massive star's core fills with iron, fusion stops and gravity wins decisively. The core collapse that follows happens so rapidly that it defies intuition. A sphere of iron with the mass of our Sun and the size of Earth shrinks to a diameter of about 12 miles in less than a second. The density increases by a factor of 100 billion, squeezing atomic nuclei together until they touch. The gravitational potential energy released during this collapse exceeds the binding energy of all the atomic nuclei in the core combined. Most of this energy goes into creating neutrinos, nearly massless particles that interact so weakly with matter that they can escape from the core even under these extreme conditions. About 10 to the 58th power neutrinos are created during core collapse, carrying away 99% of the energy released. The remaining 1% drives the supernova explosion that destroys the star and scatters heavy elements into space. The explosion mechanism itself remains one of the great unsolved problems in astrophysics. Computer simulations struggle to reproduce successful explosions because the shock wave created by core bounce typically stalls before it can blow away the star's outer layers. Recent models suggest that neutrino heating and magnetic fields might provide the additional energy needed to revive the stalled shock, but the details remain uncertain. What we do know is that supernovae are essential for cosmic evolution. They create and distribute elements heavier than iron through rapid neutron capture processes that can't occur anywhere else in the universe. Gold, platinum, uranium, and dozens of other heavy elements are forged in the incredible neutron flux that exists during the first few seconds of a supernova explosion. The supernova also creates and accelerates cosmic rays, high-energy particles that travel through interstellar space at nearly the speed of light. These cosmic rays play crucial roles in galactic evolution, heating and stirring interstellar gas, triggering star formation in molecular clouds, and possibly contributing to biological evolution through their mutagenic effects on DNA. But supernovae are not the only source of heavy elements. We now know that neutron-star mergers, those incredibly violent collisions we discussed earlier, produce about half of all elements heavier than iron. The neutron-rich environment created when two neutron stars spiral together provides ideal conditions for rapid neutron capture, creating elements that are difficult or impossible to produce in supernova explosions. The recent detection of gravitational waves from neutron-star mergers has allowed astronomers to observe this cosmic alchemy in real time. The collision designated GW 170817, detected in August 2017, produced about 10 Earth masses of gold and platinum, along with similar quantities of other precious metals. The radioactive decay of these freshly forged elements powered a kilonova explosion that glowed for weeks, allowing telescopes around the world to study the birth of heavy elements. These observations revealed that the universe's supply of gold, platinum, and rare earth elements depends on some of the most violent events in cosmic history. Every gold atom in your jewelry, every platinum atom in catalytic converters, every neodymium atom in powerful magnets was created in the neutron-rich hell of a neutron star collision and somehow found its way to Earth through billions of years of cosmic evolution. The fact that Earth contains these elements at all represents another layer of cosmic fine-tuning. Our planet formed in the outer regions of the solar system, where temperatures were cool enough for volatile compounds to condense into solid particles, but the heavy elements we depend on for technology, and possibly for life itself, had to be delivered through a complex process involving planetary migration, asteroid impacts, and perhaps cometary bombardment. The story of how Earth acquired its water illustrates the complexity of planetary assembly. Hydrogen and oxygen are abundant throughout the universe, but liquid water requires a delicate balance of temperature and pressure that exists only in narrow regions around stars. Earth orbits within the Sun's habitable zone, but whether it formed with its water or acquired it later remains an active area of research. Measurements of the deuterium to hydrogen ratio in Earth's oceans provide clues about water's origin. This ratio differs slightly between different reservoirs in the solar system, allowing scientists to trace the sources of Earth's water. The evidence suggests that some water came from asteroids, which have deuterium ratios similar to terrestrial water, while some might have come from comets, which typically have higher deuterium ratios. The delivery mechanism matters because it determines not just how much water Earth received, but also when it arrived. If most of Earth's water came from cometary bombardment during the late heavy bombardment about 4 billion years ago, then life might have had to start over multiple times as impacts sterilize the planet's surface. If water was incorporated during planetary accretion, then stable surface conditions might have existed much earlier. The timing of water delivery also affects the development of plate tectonics, the process that recycles Earth's crust and regulates its climate over geological timescales. Water acts as a lubricant in the mantle, allowing plates to move and subduct. Without adequate water, Earth might have developed a stagnant lid, like Venus, where heat builds up under the surface until it's released in catastrophic global resurfacing events. Plate tectonics, in turn, drives the carbon cycle that keeps Earth's climate stable over billions of years. Carbon dioxide released by volcanoes is gradually removed from the atmosphere by weathering reactions that depend on the exposure of fresh rock by tectonic processes. This negative feedback system has prevented Earth from experiencing the runaway greenhouse effect that turned Venus into a hellish world with surface temperatures hot enough to melt lead. The stability of Earth's climate also depends on the presence of our unusually large moon, which stabilizes the planet's rotational axis and prevents dramatic climate swings. The moon probably formed from debris created when a Mars-sized object collided with the early Earth, an event so violent that it melted both planets and created a magma ocean that took millions of years to solidify. This giant impact had to occur at just the right time, with just the right energy and angle, to create a moon with the right size and orbital properties to stabilize Earth's rotation. If the impact had been too small, no moon would have formed. If it had been too large, the debris might have fallen back to Earth or escaped into space entirely. The impactor's composition also had to be similar to Earth's mantle to explain the moon's chemical properties. The giant impact hypothesis explains many features of the Earth-Moon system, but it also highlights how contingent our existence is on rare and violent events. If the collision had happened differently, or not at all, Earth's evolution would have followed a completely different path. The stable climate that allowed life to evolve and thrive might never have existed. Even with all these favorable conditions in place, the origin of life itself represents another extraordinary transition that we're only beginning to understand. The gap between complex chemistry and the simplest living systems is enormous, involving the spontaneous emergence of self-replication, metabolism, and evolution. Recent research has identified several possible pathways from chemistry to biology, but each faces significant challenges. The RNA world hypothesis suggests that self-replicating RNA molecules preceded DNA and proteins, but synthesizing RNA from simple chemicals under prebiotic conditions proves difficult. The metabolism-first hypothesis proposes that complex chemical networks developed before genetic replication, but explaining how these networks could evolve without heredity remains problematic. Laboratory experiments have shown that some of the building blocks of life can form under conditions that might have existed on the early Earth. Amino acids, the components of proteins, can be synthesized from simple gases when exposed to electrical discharges or ultraviolet radiation. Nucleotides, the building blocks of DNA and RNA, can form under certain chemical conditions, though the process requires precise control of pH and mineral concentrations. But assembling these components into functional biological systems requires overcoming what researchers call the concentration problem. The early oceans would have been extremely dilute solutions of organic molecules, making it unlikely that complex structures could assemble spontaneously. Some researchers propose that life began in concentrated environments like hydrothermal vents or tide pools, where evaporation could increase molecular concentrations to levels where complex chemistry becomes possible. The hydrothermal vent hypothesis has gained support from the discovery of complex ecosystems around deep-sea vents that derive energy from chemical reactions rather than sunlight. These environments provide sources of energy and concentrated chemicals that might have been essential for life's origin. The mineral surfaces around vents might also have acted as catalysts, speeding up chemical reactions that would otherwise be too slow to sustain life. Alternative hypotheses place life's origin in other environments, from Darwin's warm little pond to subsurface rock formations where radioactive decay provides energy for chemical reactions. Each environment offers different advantages and faces different challenges in explaining how non-living chemistry transitioned to living biology. What's remarkable is that once life did emerge, it quickly diversified into forms that could survive in almost every environment on Earth. Microorganisms have been found thriving in boiling hot springs, freezing Antarctic valleys, highly acidic mine drainage, salt crystals, and deep underground rock formations. This extraordinary adaptability suggests that life, once started, is remarkably robust and creative in finding ways to extract energy from its environment. The evolution of complex life, however, required additional breakthroughs that might be much rarer than the origin of life itself. The transition from simple prokaryotic cells to complex eukaryotic cells with nuclei and organelles probably occurred through endosymbiosis, where one microorganism began living inside another in a mutually beneficial relationship. The evidence for endosymbiosis comes from the structure and genetics of organelles like mitochondria and chloroplasts, which retain their own DNA and reproduce independently of their host cells. These organelles are clearly descended from free-living bacteria that were incorporated into larger cells billions of years ago. But endosymbiosis requires overcoming the natural tendency of different species to compete rather than cooperate, making it a potentially rare event in cosmic history. The evolution of multicellularity represents another major transition that might be uncommon elsewhere in the universe. While simple multicellular organisms evolved many times on Earth, complex multicellularity with specialized cell types and coordinated development evolved much less frequently. The genetic and developmental mechanisms that allow billions of cells to work together as a single organism required innovations in cell signaling, gene regulation, and programmed cell death that took billions of years to evolve. Sexual reproduction, which dramatically accelerates evolution by mixing genetic material from different individuals, also represents a puzzle. Sexual reproduction is costly because it requires organisms to find mates and reduces the number of offspring that carry an individual's genes. Yet sex evolved early in the history of complex life and has been maintained despite its costs, suggesting that it provides advantages that outweigh its disadvantages. The most likely explanation is that sexual reproduction helps organisms adapt to changing environments and resist infections by constantly creating new genetic combinations that pathogens haven't encountered before. In a universe where conditions are constantly changing and where different species are locked in evolutionary arms races, sexual reproduction might be essential for long-term survival. The evolution of intelligence represents yet another transition whose likelihood we can only guess at. On Earth, nervous systems evolved independently many times, but complex brains capable of abstract reasoning appear to be much rarer. Even among species with large brains, only a few have developed the kind of intelligence that allows for cumulative cultural evolution and technology. Human intelligence seems to depend on specific features of brain organization, including the expansion of the prefrontal cortex, changes in neural development that extend the period of brain growth, and modifications to vocal anatomy that allow for complex language. These changes occurred relatively recently in evolutionary history and might represent unlikely events that could easily not have happened. The fact that human-level intelligence evolved only once on Earth, despite billions of years of evolution and millions of species with nervous systems, suggests that it might be extremely rare in the universe. This could help explain the Fermi paradox. Perhaps intelligence capable of building civilizations and exploring space is so unlikely that it has emerged only a few times in the observable universe. But even if intelligence is rare, the universe is so vast that it might contain many civilizations separated by distances so great that they never encounter each other. The observable universe alone contains at least 10 to the 24th power stars, and if the universe is truly infinite, then it contains infinitely many opportunities for intelligence to evolve. The search for extraterrestrial intelligence continues to evolve as our understanding of possible biosignatures and technosignatures improves. Future space telescopes will be able to analyze the atmospheres of potentially habitable planets, looking for combinations of gases that might indicate biological processes. The simultaneous presence of oxygen and methane, for example, would be difficult to explain without life, since these gases react with each other and must be continuously replenished. More advanced civilizations might leave technosignatures that we could detect even if they're not trying to communicate with us. These could include artificial illumination on the night side of planets, atmospheric pollution from industrial processes, or large-scale engineering projects that alter the light from their stars. Some researchers have proposed looking for Dyson spheres, hypothetical structures that advanced civilizations might build around their stars to capture energy. The recent discovery of interstellar objects like Oumuamua has raised the possibility that we might find artifacts from other civilizations right here in our solar system. Oumuamua's unusual properties, including its elongated shape and unexpected acceleration, sparked speculation that it might be artificial, though natural explanations are more likely. As we continue searching for signs of other intelligence in the universe, we're also grappling with questions about the future of intelligence on Earth. Human civilization has reached a point where it can influence planetary systems and potentially spread beyond Earth, but it faces challenges that could determine whether intelligence has a long-term future in this part of the universe. Climate change, driven by the release of greenhouse gases from burning fossil fuels, represents perhaps the most immediate threat to the stability of human civilization. The Earth's climate system has been remarkably stable during the period when human civilization developed, but geological evidence shows that it can shift rapidly between different states when pushed past critical thresholds. The current rate of greenhouse gas increase is unprecedented in Earth's history, occurring much faster than natural climate transitions of the past. This rapid change doesn't give ecosystems time to adapt, potentially leading to widespread extinctions and ecosystem collapses that could undermine the natural systems that human civilization depends on. But climate change is just one of many challenges that could affect humanity's long-term prospects. The development of artificial intelligence might lead to transformations in human society that are as profound as any in our species' history. If we succeed in creating machines that are more intelligent than humans, the future of intelligence on Earth might be determined more by our artificial successors than by biological evolution. Nuclear weapons continue to pose existential risks to human civilization, with thousands of warheads maintained by multiple nations in various states of readiness. A large-scale nuclear war could not only kill hundreds of millions of people directly, but also trigger a nuclear winter that could disrupt global agriculture and lead to mass starvation. Biotechnology advances might create new risks as they make it easier to engineer dangerous pathogens or enhance existing ones. An engineered pandemic could potentially be more devastating than any natural disease, especially if it combined high transmissibility with delayed symptoms that allow it to spread before detection. These risks highlight the fragility of intelligence in the universe. Despite all the cosmic fine-tuning that allowed consciousness to emerge, intelligent civilizations might typically destroy themselves soon after developing advanced technology. This could explain why we see no signs of advanced aliens. Perhaps most civilizations fail to navigate the dangerous transition from planetary to cosmic intelligence. But there's also reason for optimism. Human intelligence has proven remarkably adaptable, finding solutions to challenges that once seemed insurmountable. The same scientific understanding that reveals cosmic risks also provides tools for addressing them. Our growing awareness of our cosmic situation might help us make wiser choices about how to use our technological capabilities. The story of the universe is still being written, and conscious observers like you are not just passive readers of that story, but active participants in determining how it unfolds. The decisions made by intelligent beings over the coming centuries might determine whether consciousness continues to exist and flourish in this cosmic epoch, or whether it represents a brief and ultimately unsuccessful experiment in self-aware matter. In contemplating these possibilities, we return to the fundamental mystery of consciousness itself. The fact that the universe has evolved observers capable of understanding their cosmic situation represents something genuinely unprecedented in natural history. For nearly 14 billion years, cosmic evolution proceeded without any witness to observe or comprehend it. Now, in at least this one corner of the universe, matter has organized itself into patterns that can contemplate the entire cosmic story from the Big Bang to the heat death of the universe. This emergence of cosmic self-awareness might be the most significant development in the history of the universe, more important than the formation of the first stars, the assembly of galaxies, or even the origin of life itself. Through your consciousness, the universe has developed the capacity not just to exist, but to understand its existence, to appreciate its beauty, and to ponder its ultimate meaning and purpose. That makes you far more than a casual observer of cosmic evolution. You are the universe awakening to itself, matter transcending its apparent limitations to achieve something that might be genuinely unprecedented in natural history. The thoughts you think about the cosmos represent the cosmos thinking about itself. The wonder you feel at the scale and complexity of existence represents the universe marveling at its own magnificence. And that might be the most profound fact that they never taught you in school. You are not separate from the universe you observe, but rather its most remarkable creation, its greatest achievement, and perhaps its best hope for a meaningful future. In understanding the cosmos, you complete a circle that began with the first quantum fluctuations in the primordial vacuum and culminates in conscious minds capable of comprehending the entire magnificent story. The universe has waited 13.8 billion years for this moment of recognition. What happens next is up to you. If you enjoyed the video, please don't forget to like and subscribe for more amazing space paradox stories.